You are listening to The Vocal Technologist. Spoken tech for your ears.
If you work in data or really anywhere in infrastructure, you know that trying to keep up feels less like staying on top of a trend and more like, I don't know, chasing a lightning bolt.
Oh, absolutely.
Mhm.
I mean, the architectural assumptions that we all just took as gospel for the last decade,
Mhm.
things about distributed systems, eventual consistency,
Yeah,
they're just being broken
yeah.
at an incredible rate.
It's true. I feel like we've hit this inflection point where the trade-offs between performance and complexity are just fundamentally changing the whole equation for engineers.
It's not just like a 10% improvement anymore. We're seeing changes that let really small teams handle just massive scale and cheaply.
Absolutely. And since this is Product Thursdays for data, we've been looking at some fascinating stuff coming from the, let's say, the front lines of innovation. What
Sure.
giants like Netflix and LinkedIn are building,
Right.
how single node databases are suddenly challenging these huge distributed clusters, and maybe the most interesting part, how AI is being built right into the query layer itself.
Yeah, our exploration today is really focused on those critical shifts. We're going to get into the move toward modular AI, the surprising power of single node architecture, and how these core database systems are engineered to just instantly retrieve massive amounts of data.
To feed those recommender systems.
Exactly. We want you to walk away from this understanding not just what's new, but why these shifts actually matter to your bottom line and your team's efficiency.
Okay, let's unpack this, and let's start where a lot of the modern complexity lives, which is personalization and, of course, large language models. Netflix is taking a really strategic approach here.
They are. They're centralizing their whole personalization strategy around one large foundation model.
Which is smart.
It is, because it standardizes the core learning about user preferences across the entire company. But what's really insightful is that they don't force every single application, the title screen, the search bar, whatever, to consume that data in the same way. They actually support 3 distinct integration patterns in production to meet these really diverse application constraints.
Right, and I bet those patterns reveal that eternal struggle, between freshness and accessibility. When you have petabytes of data, speed often means making a compromise somewhere.
That's it exactly.
So what are those 3 patterns, and maybe more importantly, what pushes an engineering team to choose one over the other?
Well, they range in complexity. So the simplest one is batch refreshed embeddings. These are typically stored in a big, scalable embedding store. It offers fantastic low latency access at enormous scale.
But the data is calculated periodically, so it's fast, it's cheap to retrieve, but my prediction might be based on what I liked yesterday, or maybe even last week.
That's the exact trade-off.
So if the other patterns give better quality, why would anyone ever choose the stale batch pattern?
Because the cost and complexity of real-time lookups can be prohibitive. I mean, think about applications like personalized email campaigns or generating static homepage segments.
Right, doesn't need to be up to the second.
Exactly. Batch refreshing gives you, say, 90% of the personalization value for maybe 1% of the compute cost and operational headache. It's the pragmatic choice.
Makes perfect sense. The complexity budget is a real thing. What's the next step up?
Moving up, they offer subgraph integration. This is where you're pulling features directly from the underlying interaction graphs and feeding them into the model in real time.
Okay, so that unlocks the deeper real-time stuff, the freshest personalization possible.
It does, but you pay pretty significant tax for it in complexity, in latency, and compute cost for every single request.
So that's the gold standard. You only use that when latency is absolutely critical, like for real-time suggestions as you're scrolling.
Precisely. And the third pattern is a bit simpler. Customized, fine-tuned model deployments. Just smaller, tailored models for niche applications.
The real key here seems to be the modularity of the whole framework.
That's the insight. It lets data teams tailor their approach based on the application's budget for latency, complexity, and cost, instead of, forcing a one-size-fits-all monolith on everyone.
Right. And of course, models, whether they're centralized or fine-tuned, are pretty useless unless you can feed them features instantly. Which pulls us down into the foundational infrastructure.
The system's designed for that instant delivery at global scale.
Let's talk about LinkedIn and FishDB.
FishDB is LinkedIn's generic retrieval engine. It's really a cornerstone of their recommender systems, including the main feed. And the fact that it's written in Rust tells you everything you need to know.
Performance and memory safety?
Maximum performance and memory safety.
We hear about Rust all the time in high-performance computing. So given the sheer volume of activity on LinkedIn, how does FishDB architecturally even manage that flood of requests?
It uses an extremely efficient and classic scatter-gather model. A query comes in, find me 10 posts relevant to this user, and a central broker distributes that query.
It scatters it.
It scatters it across 48 sharded partitions instantly.
Yeah.
And for fault tolerance, each of those 48 partitions has 16 replicas.
Whoa, 48 partitions, 16 replicas each. That is some intense parallelism. So the scatter-gather approach ensures no single machine is a bottleneck.
Exactly. And your latency is just capped by the slowest partition to respond. And internally, efficiency is just paramount. FishDB relies really heavily on in-memory indexes.
Inverted forward reference indexes.
All right, all engineered for two specific things.
Yeah.
Low indirection and copy on write updates.
Hold on, let's make sure we clarify those for everyone listening. What does low indirection actually get you? What does it let FishDB do?
Low indirection just means the system minimizes the steps needed to look up a piece of data. So instead of going through multiple layers of pointers or tables, which adds milliseconds, it just accesses the memory location directly. It's all about maximizing cache efficiency.
Got it. Direct access is fast access. And what about copy on write?
Copy on write is crucial.
Yeah.
It lets you maintain consistency without locking the whole system during an update. When new data comes in, it makes an atomic copy of just the index segment being changed, applies the write there, and then swaps it in.
So the system can handle a constant stream of updates while still serving massive read traffic with, minimal interruption.
That's it. It's foundational engineering in action.
Okay, so to handle the really complex, layered feature requests that a feed like LinkedIn's generates, you mentioned a specialized mechanism.
Yes, it uses a Volcano-style query engine.
A Volcano-style engine.
Yeah, this type of engine is essentially a query planner. It models the whole process as a tree of operators, which allows it to interpret really complex expressions.
And why is that so crucial for a recommender system?
It lets them dynamically interpret sophisticated feature logic. For instance, something like, show me content where the user's skills intersect with the post's topic, but only if they haven't seen something from this person in the last 24 hours.
Right, a really complex set of rules.
And the Volcano engine just orchestrates that complex filtering and ranking logic at retrieval time, so the model can deliver these highly nuanced results instantly.
So if you're just scrolling through your feed, the system is doing all this frantic multi-shard coordination and complex query planning in milliseconds.
That foundational speed is what allows the intelligent agents running on top to even function at all.
Which is the perfect transition, because that kind of speed is now being paired with what's called context engineering to make AI agents smarter.
And more reliable.
Right. AI agents are the hot topic, but they can easily suffer from, token anxiety, they get overwhelmed. Dropbox had this issue, and they had to dramatically improve their AI assistant Dash through better context management.
And what we were looking at highlighted that this is, at its core, a resource problem. Better agent performance often isn't about better prompting. It's about ruthlessly managing the token budget.
Making sure the agent only gets highly valuable context.
Exactly. And they focused on 3 key strategies to do that.
Okay, let's hit the 3 big wins for Dash.
First was tool consolidation. They used to have a bunch of granular retrieval tools, one for docs, one for slides, one for cloud storage.
Yeah.
They combined all of them into a single unified Dash search tool, and that immediately reduces tool sprawl.
That makes so much sense. You just simplify the decision tree for the agent. If it has to decide between 6 different ways to get data, it wastes time and tokens just choosing the path before it even asks the question.
Exactly right. The second strategy was knowledge graph filtering. So instead of just dumping raw search results into the agent's context window, they use an underlying knowledge graph to filter those results at runtime.
So the knowledge graph is like a semantic bouncer.
That's a great way to put it.
It's only letting the most relevant context into the agent's precious context window.
That's the function. It just cuts down on all the extra detail that might otherwise lead the agent to, hallucinate or just waste tokens debating irrelevant facts.
And the third strategy was about delegation.
The third is delegation. So for complex subtasks, like constructing the perfect, most specific search query from a user's, rambling request,
Right.
they delegate that subtask to a specialized search agent. This whole approach, consolidation, filtering, and delegation, it effectively balances cost, latency, reliability, and token usage. And it led to massive performance gains.
That kind of structural discipline feels like the engineering maturity we've been waiting for in the LLM space, which raises a fascinating question. If agents need this level of engineering, what tasks are actually suitable for this new agentic AI paradigm?
Agentic AI really shines in complex, reasoning-heavy tasks. Think about things that are repetitive or highly expert-dependent or require pulling together scattered, unstructured data.
They're expert automation tools, not generalists.
Right. They can dramatically cut down human effort, but they are not magic.
And you emphasize there's one non-negotiable requirement for this to work.
Yes. Success depends entirely on having a clearly bounded scope. If the agent's job is ambiguous, if it doesn't know exactly where its limits are, it will fail. You need well-defined tools, which might mean building sub-agents, and enough upfront documentation to eliminate any ambiguity.
Bounding the scope is the key. Okay, let's pivot to some of those fundamental architectural assumptions that are breaking. For years, the mantra for scalable systems was just accept eventual consistency. It was the necessary sacrifice.
And that sacrifice causes so much friction for developers. Eventual consistency forces them to write this incredibly complex defensive code. You have to manage sophisticated routing, write manual retry loops, build reconciliation logic.
Just to deal with stale data that shouldn't even be there.
It shouldn't.
Wow.
Developers end up writing consistency hacks instead of business logic, and that's a huge drain on productivity.
But the analysis we reviewed suggests that modern systems are making a very strong case for returning to strong consistency, even at massive scale.
They absolutely are. Take Aurora DSQL as a prime example. It achieves strong consistency across all of its replicas, which is a massive simplification for developers.
Yeah.
It manages this by combining monotonic journal updates with timestamp-based queries.
Okay, let's focus on the monotonic journal updates. That means every change happens in a strict, defined order, right?
Functionally, yes. Every single write is guaranteed to be applied in the exact same sequence across every replica.
Yep.
So when a replica gets a read request, instead of just checking its local state and maybe returning stale data, it just waits.
It waits for what?
It waits for the monotonic journal to confirm that all prior writes relevant to that query have been fully applied.
So the application developer doesn't need to worry about the database returning old data anymore. This one architectural guarantee just removes an entire class of painful, high-cost errors.
Race conditions, stale reads, all of that goes away.
Right.
It frees up the development team to focus purely on the application logic. It's a massive win.
It simplifies the entire stack.
Yeah.
Okay, here's where we challenge a really massive assumption, one that I think is fundamentally changing the role of the data engineer. For years, the big data community preached that if your data set gets too big for memory, you must use a distributed cluster. PySpark, Hadoop, you name it.
That orthodoxy is being demolished.
Yeah.
And it's mostly because single-node engines are just getting so much better at using the available local resources. We saw testing on a huge lakehouse dataset, 650 gigabytes of Delta Lake data,
Okay.
running on a surprisingly modest commodity cloud machine. A 32 gig EC2 node?
650 gigs on a machine with only 32 gigs of RAM. That requires some fantastic memory spilling and management, so what did the results show?
They were shocking. The data really speaks for itself. Polars, running on that single node, completed a full aggregation in just 12 minutes. DuckDB, another single-node SQL engine, finished in 16 minutes.
12 in 16 minutes, that's really fast. So what about PySpark, the established distributed choice?
PySpark, running on a cluster configured for this workload, took over an hour.
Wait, hold on. A single node engine on one cheap machine beat a large, complex, distributed cluster by a factor of 5. That is an enormous consequence.
It is.
We're talking massive cost savings, massive reduction in operational complexity.
That is the big takeaway. Thanks to vastly improved larger-than-memory support, these single-node engines can handle datasets that previously demanded a cluster. You eliminate the cost of coordination, the complexity of scaling, the nightmare of debugging distributed code.
So for most analytical workloads under, say, a terabyte, a distributed cluster is no longer a technical necessity. It's an operational choice.
It's become a choice, not a requirement.
That's the real headline here for the vocal technologist audience. You can move faster, you can slash your cloud spend, and simplify your code all at the same time. This just fundamentally changes the investment calculus for every data platform team.
And speaking of efficiency, let's talk automation and data ops. Tools designed to make teams faster without, exploding those newly optimized cloud costs.
So what's making the biggest impact on orchestration efficiency?
The dbt Fusion engine is a really good example. It directly tackles that trade-off between moving fast-running pipelines frequently and managing your cloud spend.
And how does it give teams both of those things, speed and cost control?
It uses what's called state-aware orchestration. So before it kicks off a pipeline, it intelligently scans the environment and automatically skips any models and tests that haven't had their upstream dependencies updated since the last run.
So it's not just rerunning the entire DAG because I changed one variable in one tiny table.
Precisely. This smart, selective execution, it's demonstrated 29% efficiency gains in real-world environments while totally maintaining data freshness. It just eliminates that brute force processing.
That's a powerful argument. Using intelligence in your tooling rather than just relying on brute force computation or scaling up the hardware.
Right. And now let's turn to the final layer, SQL itself. The language everyone uses is evolving to be both simpler and, well, smarter.
On the simplicity front, we've got an upcoming standard feature, GRUP by all.
Yeah, this is coming in the SQL.GUI standard, and it's a huge quality of life improvement. It automatically groups your query by every non-aggregate expression in the select list.
So no more manually repeating dozens of columns in the group by Y clause,
It just eliminates all that manual repetition for typical analytical queries.
which cuts down on so much friction in typing. But what's the caution here? I mean, sometimes a boilerplate exists for a reason.
The caution is simple, but it's crucial. It's about clarity. If you adopt this, any future change you make to your select list adding or removing a column implicitly changes your grouping criteria. And in a complex, evolving codebase, that implicit change can lead to some real confusion if developers aren't expecting it.
It shifts the complexity from the bottom of the query to the top. Use with care.
Use it carefully.
Okay, let's talk about the intelligence upgrade. This is where AI moves from being something external, you call, to something fully integrated into the data layer.
BigQuery is really pioneering this with managed AI functions like AI.if, AI Classify, and AI Score. And these functions use powerful LLMs like Gemini, but they're executed directly by the database engine itself.
So what does that enable? I can literally use AI inside a SQL query.
Absolutely. You can now do direct semantic filtering, classification, and ranking of unstructured data inside your standard SQL. So for example, you can select product reviews, and in your where clause, you can use AI Classify, review text, positive, negative, neutral, equals negative.
To filter out just the negative review.
Or use AI Score in an order by clause to rank them by how positive or negative they are.
That is game-changing. It eliminates the entire historical ETL step of needing to manually pre-process data through a separate NLP model just to enrich it. The intelligence is just baked right in.
You're eliminating the manual prompt tuning, the model deployment, the synchronization headaches. You're empowering analysts to access and infer meaning from unstructured data directly at scale.
This entire view we've explored, I mean, from Netflix's modular models to integrated AI functions in SQL, it really confirms that data value doesn't grow linearly anymore. It compounds through connection.
It absolutely does. The pattern we're seeing is this data flywheel, where value accelerates not through siloed products, but through these highly interconnected data ecosystems. The priority now is connection density and context-driven design.
Because the more connected your data is, the faster your learning loop becomes.
Exactly.
Yeah.
And that connectivity implies a different way of structuring that data to begin with. We talked about knowledge graphs earlier with Dropbox, and they offer these distinct advantages over relational systems for modeling highly interconnected domains.
Right.
Once you cross a 30-table threshold, traditional schema evolution becomes a nightmare. Knowledge graphs simplify that, and they enable advanced inferencing, which is crucial for maximizing that flywheel effect.
This has been a fascinating look at how complexity is giving way to this engineered simplicity. It leaves me with one big question, though. If single-node engines are now powerful enough for hundreds of gigs at a fraction of the cost, and LLMs are built right into SQL, what happens to that historical boundary between a data engineer and a machine learning engineer?
Is the job role itself becoming one integrated AI-first position?
Where the old barriers of scale and model deployment just kind of dissolve away?
That is certainly the question the industry is going to have to grapple with as all these efficiencies become the norm.
Something for you to mull over as you contemplate your next architecture refresh. Thanks for joining us for this analysis of the next generation of data architecture. We'll catch you next time.
Spoken Tech for your ears.